Until now, we've been talking about orbitals in the hydrogen atom. Now we're ready to expand that to every other kind of atom. And it won't be a big jump because for polyelectronic atoms, atoms with more than one electron, the orbitals are the same shape as they were for hydrogen. There will still be 1s orbitals that are spherical. There will still be p-shaped orbitals that are dumbbell-shaped, and so on and so on. So if we look at a qualitative sketch, it won't look very different. But if we were trying to quantify the energies of the orbitals, the energies would be very different. And there's a couple of reasons why. First of all, let me talk about the atomic number of these different atoms. Z stands for the atomic number, or the number of protons in the nucleus. The number of protons is going to affect the energy of electrons moving around it. The higher the positive charge, the more attraction for the electrons in the orbitals, and therefore the lower energies the orbitals have. But it's not even that straightforward, because the electrons don't all see the full positive charge on the nucleus, and that's why I've shown a different symbol here, a Z star, for the effective nuclear charge. The effective nuclear charge is the charge the electron feels, whereas the atomic number is the actual full positive charge. Why aren't they the same? Because valence electrons are screened from the nucleus by core electrons. Now there's some terms I have to define in red. Valence electrons are the ones in the highest occupied energy level. In highest occupied, N for short, highest occupied energy level. You remember, the higher the energy level, the further the electrons are from the nucleus, probably. That's in contrast with the core electrons. Those are the rest of the electrons. So let me show you an example. I'm going to start with a pretty simple atom. I'll pick boron, which is atomic number 5. And I'm going to make a sketch. Humans like to visualize things. I'm going to go back one model to the Bohr model and make a nice simple sketch. It's not uncommon to use a simpler model, even though we know the quantum mechanical atom is more complicated than that. I'm going to use the model that's going to let me see what I need to see. So boron's atomic number 5. It's got 5 protons in the nucleus. And I'm going to show an orbit instead of an energy level, even though I don't really believe in those anymore. Now, I'm trying to show where the electrons live in the boron atom. In a neutral atom, the number of protons and electrons are equal, so I'm going to have to place 5 electrons here. But how many can I put in the first energy level? The only orbital at the first energy level is the 1s, and the Pauli exclusion principle says I can only put a maximum of 2 electrons in it. So at the first energy level, I can only show 2 electrons. I'm going to have to go to the higher energy level to find room for more. There are 3 more electrons I have to place. How many do I have room for in the second energy level? Well, in the second energy level, there are 2 squared, or 4 orbitals. I can hold 2 electrons apiece. That's room for 8, but I don't need room for 8. I only need room for 3. So there's a nice simple sketch I can draw anytime I want to visualize the atom. What I can see here is an illustration of valence versus the core, the electrons on the inside. Now the atomic number for boron is, of course, 5. It's got 5 protons in the nucleus. But the effective nuclear charge, the charge that the valence electron sees, is 5 for the protons, but that's canceled out by the 2 electrons in the core. So the net charge that the valence electron sees is only 3+. So that's going to affect the energy of the different sublevels. The core electrons see the full nuclear charge. There's nothing in the way between the ones in the first energy level. But the valence ones will only feel a net charge of 3, and that will change their energies. Here's another thing. Now, this was the Bohr model. Now I'm going to go to the more detailed quantum mechanical model. Not only are the absolute values of the energy levels different in polyelectronic atoms, in polyelectronic atoms, the sublevels are no longer degenerates. In other words, the 2s is not the same energy as the 2p in any atom except hydrogen. And here's the reason why. I've got a graph here. I've shown you something similar to this before. That complicated function was just a measure of the probability of finding an electron. And on the x-axis, we've got the distance from the nucleus. If I look at the blue line, that's the 3s. And what we saw for the s orbitals is that other than the first one, I have nodes in them. So for the blue curve, there's a node and there's a node. There are 2 distances from the nucleus where you can't find an electron in the 3s orbital. Now let's look at the 3p orbital. It's got 1 node here. The 3d orbital, represented by the green line, has no nodes. What's going to matter for me is which orbital will let an electron get closest to the nucleus, because we saw on the previous slide that the closer it is, the lower in energy that it is. It feels the attraction from the positive nucleus more. What I can see is that an electron in the 3s, that's the blue curve, can get closer to the nucleus than the other ones can. I would say that the 3s orbital penetrates closer to the nucleus. So the electrons in the 3s will feel more pull than the electrons in the 3p. And that's what I'm trying to say up here in words. The screening experienced by the electrons. You remember we said that the inner electrons hide the outer electrons from the full pull of the nucleus. They hide it, they screen it. The screening experienced by electrons in the s orbital is less than in the p orbital, is less than in the d orbital, because the penetration is greatest for the s. So now we're going to go on and look at a revised energy level diagram that will apply to every atom except hydrogen. And what I can see here on this energy level diagram, we've still got the 1s, the lowest, and then the 2s. But see, the 2p is not the same energy as the 2s anymore. For these polyelectronic atoms, the atoms with multiple electrons, the sublevels are not degenerate. All right, third energy level, the 3s is lower than the 3p, which is lower than the 3d. What you'll notice is eventually we'll get to a point where the energy levels start overlapping. The 4s is actually lower in energy than the 3d is, and I think that's kind of counterintuitive. Now we're going to have to know what order to fill these orbitals up in. When we make the ground state, we want to put the electrons in the lowest possible energy orbitals. So I'm going to briefly teach you a trick for doing that, but you know how I hate tricks. Soon I'll teach you a much better way. But we got to start somewhere. So you'll see a diagram like this in many textbooks. This one comes off the web. And the problem with pictures you see in textbooks, they look like they're completed as a done deal. You see the whole thing at once. I want to show you how you can construct this figure for yourself anytime you need it. What I'm going to do is take the names of the orbitals and list them from the bottom up. So at the first energy level, we get a 1s. At the second energy level, 2s and 2p. And I'm writing them straight across as if they were degenerate. Third energy level, 3s, 3p, 3d. Fourth energy level, 4s, 4p, 4d, 4f, and so on and so on and so on. Now, to make it relevant to a polyelectronic atom, I'm going to go diagonally through those. First, I'm going to fill the 1s. Then I'm going to fill the 2s. Then the 2p. Then the 3s. Then the 3p. Then the 4s. And I'm going to fill the 4s before I come back and fill the 3d. After 3d comes 4p. After 4p comes 5s. Keep going up and up and up. So the cool thing about that trick, it's really easy to construct anytime you want. Don't memorize the diagram on the left. It's a waste of brain space. All right, now the exciting part. Now that I know the orbital energies, I'm ready to start writing what are called the electron configurations of atoms. I'm going to show the arrangements of the electrons in an atom or ion. And we're going to start by writing the ground state electron configuration. The ground state, whoops, remember that's the lowest energy arrangement. So we're going to follow these rules, and I'm going to apply them with examples as we go. The first rule is that we're going to fill the lowest energy orbitals first. We're making the ground state, so we want to put the electrons in the lowest energy orbitals. Now that has a fancy name. That's called the Aufbau principle. That means building up in German. I don't care what it's called as long as you know how to do it. Next rule, we're going to put a maximum of 2 electrons per orbital, and they're going to have opposite spins. We've already looked at the Pauli exclusion principle. I'm going to save the third rule for later. We don't need that yet. Let's get right into it. There are various styles in which we can represent the electron configuration of atoms. The most detailed is an energy level diagram, like I showed you in the earlier slides. But that's going to take up a lot of space. So often what we do instead is called an orbital diagram. And we're going to make a box to represent the orbitals. So for example, I've got a box to represent the 1s. Now, we're going to do it for a variety of atoms. You'll need your periodic table to do this. You'll need to know the atomic number. 1, 2, 3, 4, 5. Because for neutral atoms, the number of electrons is the same as the number of protons. So I can see for hydrogen, I'm going to have to place 1 electron. It goes in the lowest energy orbital. Now I'm going to put an arrow to represent that electron. I'm done. I've run out of electrons. So I'm not showing a box for any more than the 1s. I could. All the other orbitals are available. You remember an orbital is just an empty space where I could put electrons. But to keep my diagram simple, I'm only going to show the orbitals that have electrons in them. So that's a pretty good shortcut, that orbital diagram. There's an even shorter shortcut, and lots of people call it the SPDF notation. I suspect this is going to ring a bell with some of you. What we're going to do is list the symbols for the orbital, 1s, and then I'm going to put a superscript in there to say how many electrons are in the orbital. So I would say for hydrogen, 1s, 1. That's it. So that means I have 1 electron in the 1s orbital, no matter how you look at it. All right, on to the next one. And the more I do, the more you're going to get ahead of me. If you can pause the video and run through all of these, do it. If you can pause frequently, as soon as you think you can get ahead of me at any point, pause the video and get ahead of me. Anything you can do before I get there, that means you own it and you don't have to study it later. All right, on to helium, atomic number 2. So in a neutral atom, I'm going to have 2 electrons to place. The lowest energy orbital is the 1s. Here we go. 1, 2. I've shown the 2 electrons with opposite spin, and that fills the orbital. You've noticed I didn't put the full head on the arrow. That's because I'm lazy. I didn't have to lift my pen to do that. That's quite common to use those kind of fishhook arrows. All right, that's the orbital diagram. The SPDF notation, 1s, 2. On to lithium, 3 electrons. The 1s will hold 2, but now that orbital is full. So now I need to show the next orbital, and following the order that we showed on a couple of slides ago, the next energy orbital is the 2s, sorry. So the 3rd electron in lithium goes in the 2s. I don't care if it's spin up or spin down, doesn't matter at all. The SPDF notation, 1s, 2, 2s, 1. Now, the SPDF notation isn't looking like much of a shortcut yet. If I had to draw the orbital diagram before I could draw the SPDF notation, that would get really tedious. But once we get some practice, you're going to be able to rattle off the SPDF notation without the orbital diagram. But we got to walk before we can run. Okay, beryllium, 4 electrons. 1s can hold 2, then comes the 2s, and it can hold the other 2, opposite spins. SPDF notation, 1s2, 2s2. Boron, atomic number 5, has 5 electrons in the neutral atom. The 1s will hold 2. The 2s will hold 2. But now I need room for more electrons. So I have to go back to my scheme and decide which energy level comes next. That's the 2p. P orbitals come in sets of 3. So I'm going to draw 3 connected boxes and label them 2p. All right, I need room for 1 more electron, and why not just put it in that box? It doesn't matter which box. You can put it in any of those boxes. You can put it spin up or spin down. Doesn't matter. SPDF notation, 1s2, 2s2, 2p1. All right, continuing on. Carbons, atomic number 6. Nitrogen, 7. Oxygen, 8. Fluorine, 9. And sodium, I skipped one, that's 11. For carbon, 1s can hold 2. 2s can hold, oops, that's not where that goes. 2s can hold 2. Then comes the 2p. All right, the 5th electron goes in there. Where does the 6th one go? I will finally need the 3rd rule on my list of rules. And that is here. The 3rd rule says, put 1 electron in each orbital of a sublevel before pairing the electrons. That's called Hund's rule. I don't care what it's called, I care what you do. So what that means is for carbon, I have to put the 6th electron in a different orbital, not to pair up the one in the first 2p. I half fill the sublevel before I start pairing it up. All right, here we go. SPDF notation, 1s, 2, 2s, 2, 2p, 2. Okay, now, I don't want to be tedious. Let's jump ahead. Let's go to fluorine, atomic number 9. 1s can hold 2. 2s can hold 2. The set of 2p's, here we go. I stopped counting at 4, 5, 6, 7, and now that I've half filled the sublevel, I can pair it up. 8, 9. SPDF notation for fluorine. 1s, 2, 2s, 2, 2p, 5. All right, one last one for the orbital diagrams, and then we'll just move on straight to the other kinds of notation. Sodium, 11 electrons. 1s holds 2. 2, whoops, I keep doing that. 2s holds 2. 2p. We left off counting at 4, 5, 6, 7, 8, 9, 10, and I filled the p sublevel. So now I'm going to have to go to the next energy level, and that is 3s. 3s comes in sets of 1. There's room for one more electron. SPDF notation. 1s, 2, 2s, 2, 2p, 6, 3s, 1. So there's an introduction to the electron configurations for polyelectronic atoms. When we come back, we'll practice that some more, and we'll see how it relates to the way that the periodic table is structured.